So we've learned about the orthogonality of eigenfunctions. That is to say, when you have a collection of functions which solve non-zero, which solve an eigenvalue problem, uh, the theorem that I shoved down your throat is that those eigenfunctions are what are called orthogonal. They're pairwise orthogonal in the sense that the inner product of any two of them is zero. Now, in this video, I want to say a little bit more about inner products and about orthogonality, and that's going to be these ideas are going to be very, very helpful for your life, but in particular, also very helpful for the theory of Fourier series and computing the coefficients of them. Okay, so first thing I want to say, let me just remind you, here's the definition of the inner product, and I want to establish this notation here. I want to denote this integral, the integral from a to b of x1 times x2. I want to call that the with these angular brackets x1 x2. That's the inner product notation. Okay, and what I want to do is establish some properties of this inner product. All of these properties are trivial consequences of the definition. And if any of them are mysterious to you, please come talk to me because I'm more than happy to talk about them. So the first property, it's called symmetry. Symmetry means that it doesn't matter what order you take the inner product in, you get the same number out. For all x1, x2, for all functions x1, x2, you have this situation here. Second property. What is the second property? Oh, right. This one is crucial. Bilinearity. So what on earth does this mean? This means that if I take in the first, let's say I put in the first slot here a superposition of two functions, a linear combination of x1 and x2, and I take its inner product with x3. Well, this breaks down in exactly the way that you would hope, I hope, without losing information about all of this information. So this was c1 times x1, inner product x2, x3, plus c2 times inner product of x1 with x2 with x3. I vaguely know what I'm doing. Does that make sense? In other words, we're kind of splitting up this superposition across this inner product, if you like. It's kind of like the inner product distributes over addition and scalar multiplication, and respects scalar multiplication. Okay? Now, we say this is a bilinear property, but only really in conjunction with the symmetry property, because if we only had linearity, if we only had this property in the first slot of this inner product, which has two slots, then we would say it's linear in the first slot. But symmetry means that it's also going to be true in the second slot, and so we say that it's bilinear. Bi being some kind of Greek prefix or something. Third, positive definiteness. This is the statement that if you take the inner product of x with itself for any function x, this is always going to be greater than 0 if, and only if, well, I guess it's just if x is not 0. Okay? So the inner product of a function with itself is always a positive real number. All right, those are the three properties of an inner product. And if you were to take a linear algebra class and study abstract vector spaces and study inner products on abstract vector spaces, you would find that the definition of the inner product was be any gadget which eats two inputs which satisfies these three properties, in fact. Okay, so yeah, there's a little bit of I'm calling these properties now and just making this definition and calling it the inner product. But you know, there is a continuation of this story in the world of linear algebra. In short, what this inner product does is give a notion of geometry to your vectors, and in particular for us, our functions. Okay, we can now begin to talk about things like the length of a function or the angle between two functions. We can talk about that. In particular, we can talk about when two functions kind of quote unquote have a right angle or make a right angle to one another. That's when the inner product is zero, and that's the notion of orthogonality. Okay, so in particular, we want to think about why orthogonality is so useful. Okay, orthogonality is a very special property, and we want to know why. So I want to prove to you or demonstrate to you that orthogonality is useful. Okay, so suppose that we have two orthogonal vectors. Let's call them v and w. Suppose v and w are orthogonal. Of course, what this means is that the inner product of them is zero. So v inner product with w is equal to zero. All right, and now suppose that we can write x as a linear combination, aka a superposition of v and w. And let's say it's I don't know, a times v plus b times w. Let's just say. Can we find a and b? What are some nice formulas for a and b? Can we compute a and b? In other words, can we figure out how much x points in the v direction? How much of x is v and how much of w is how much of x is w? Yeah, that's sort of the idea. We have these two vectors, v and w. They are orthogonal to one another. We kind of picture them as making a right angle, and then we have something which this other vector, which we're going to think of as being x. Maybe x is like this. How much of x? How many v's? How much v do we need to make x, and how much w do we need to make x? That's the question. That's what a and b sort of represent. All right. Well, we can do the following calculation. All right. Let's compute the inner product of x with v. Oh, and I should say here, let's say that v and w are orthogonal, and let's say they're non-zero. So these are not zero. Not the zero function. Not the stupid function where constantly equal to zero. How can we compute a and b? Well, here's one way. Let's look at x with v, the inner product with x with v. This is equal to, by assumption, av bw plus bw, inner product with v. By bilinearity, that's equal to a times the inner product of v with itself plus b times the inner product of w with v. But notice two things. This is equal to zero by orthogonality. That's what it means to be orthogonal. Oh, well, and I guess symmetry as well. Notice here, by assumption, the inner product of v with w is zero. By symmetry, that means that the inner product of w with v is also zero. Okay? Now let's think about this one. What do we know about that? We can't say a whole lot, but we can at the very least say this is not zero by positive definiteness. Right? Because v is not zero. Okay, so what that means is that we can figure out what a is. This implies the conclusion is that a is equal to the inner product with x with v divided by the inner product of v with v. Okay? Very, very, very useful, this. Okay? That we can figure out how many v's we need to create x by looking at just inner products. And similarly, by the way, we can also figure out b. This is similar. We just take the inner product of x with w and divide by the inner product of w with itself. Okay? This kind of calculation is what motivates the Fourier series story. Okay? Because the eigenfunctions, and I'll remind you, let's go back to what we did last time. The eigenfunctions that we found here, and together with this one, x of t equal to 1, together with x of t equal to cosine kt and sine kt. Turns out those are all orthogonal to one another, okay? And so what we're going to try to do is express an arbitrary vector, an arbitrary function from a to b as, well, not from a to b, but from 0 to pi, as a sort of linear combination of those infinitely many vectors. It's not quite a linear combination technically, pedantically. It's going to be an infinite series of them, but the idea is going to stay the same. We're going to use the orthogonality of those eigenfunctions together with this inner product gadget to write down formulas for the coefficients in the Fourier series. Okay, we'll do that in the next one. Okay, see you then. If I can close this video. Okay, it's the next one.